In this example, we'll analyze a simple aspect of X-ray diffraction. So we have X-ray diffraction of copper, and this copper has a face-center cubic structure. And we'll carry out this analysis with X-rays that have a wavelength of 0.154 nanometers. So in the X-ray diffraction pattern, we see at an angle 2 theta of 43.2 degrees, we see a peak. And the question is, can we determine what the Miller indices are for that peak? And so what we're going to do is we're going to use Bragg's law, which is relating the wavelength. So this is the wavelength of the X-rays. Relates that to the spacing between the planes of the planes whose Miller indices we're trying to determine, and the angle theta. So this is the interplane spacing. So I've just rearranged this equation here to solve for D, just a wavelength over 2 sine theta. We're given the X-ray wavelength. We're giving 2 theta, so theta is 43.2 divided by 2. And we calculate that the spacing, the D spacing between these crystal planes that result in this X-ray peak is 0.209 nanometers. So then we need to use a relationship that basically comes from geometry, and that says the spacing between planes with Miller indices H, K, and L is equal to, for face-center cubic structure, unit cell dimension over H squared plus K squared plus L squared. So H, K, and L are the Miller indices. This is the unit cell dimension, and for a face-center cubic, the unit cell dimension is equal to 2 times the atomic radius times the square root of 2. And this is also just from geometry if we look at the crystal structure. So R is the atomic radius. That's something we can look up, for example, in a periodic table, and its value is 128 nanometers. So we know the atomic radius. That means we can calculate A. We know D is equal to 0.209 nanometers. So we can solve for H squared plus K squared plus L squared. So here's substituting the atomic radius. We now have the unit cell dimension. We substitute that in here, and so we can calculate the square root of H squared plus K squared plus L squared. And that's A over DHKL. So I've substituted in the values that were calculated, the unit cell dimension, interplane spacing, get the square root of the values. We square both sides. H squared plus K squared plus L squared is equal to 3. Now we need to use some additional information about face-center cubic structure, namely that the principal diffraction planes, so it's the main ones that would show up, the principal diffraction planes are those whose indices are all even, all odd. So that means 111, 200, 220, all odd, all even. Those are the only ones that are going to show up as the main peaks. What values of H, K, and L that are even or odd give us 3.0 when the sum of the squares? Well, clearly, if one of these is 1, we couldn't have a higher number, we're going to be much larger than 3. If it's 2, any of them for even, be much larger than 3, even if the others are 0. So the only possibilities are that H equals K equals L equals 1. The sum of squares is 3. And so this diffraction peak then is the 111 plane. This is the close packed plane, the hexagonal symmetry plane in the face-center cubic structure. So this is face-center cubic structure, the 111 plane that we obtain its location in the X-ray diffraction pattern, and we can back out by Bragg's law and geometry.